Adam Muth.
And I'm Tyler Thur, and we're part of Mr. Collier's Period 3 Accelerated Physics class.
Our topic today is great follies and famous conversion mistakes.
As we asked, we're going to start off with a question that provides creative considerations and fascinating ideas to provide deeper, more exciting, and inspirational thought. We know that this might not be the most exciting topic in the world, but hopefully it will be interesting and hopefully it will be able to save you some points on future quizzes. With that, our question is how to prevent these future conversion mistakes and how to avoid them risking life, or how to avoid them risking serious consequences to construction projects. Though maybe it seems like these only affect how many points you get on a quiz, we will prove through future examples that these have put human lives at risk and they're important to prevent. Our first example comes from NASA. On September 23, 1999, NASA lost the $125 million Mars Climate Orbiter satellite after a 286-day journey to Mars. Miscalculations due to the use of English units instead of metric units apparently sent the craft off course over 60 miles. Thrusters used to help point the satellite had, over the course of months, been fired incorrectly because data to control the wheels were calculated in incorrect units. This was significant because when the orbiter entered the atmosphere, it disintegrated, and NASA was no longer able to measure climate or scientific calculations necessary to colonize or explore Mars. Through the use of a problem, we will demonstrate how they could have avoided this. So, obviously NASA had quite the problem in calculating how many pounds of thrust there were for the Mars Climate Orbiter. But the real question is why this happened. Well, evidence indicates that Lockheed Martin, which was performing the calculation, was sending in thruster data in English units, or pounds, to NASA, while NASA's navigation team was expecting metric units. Instead of considering the circumstance, they just assumed that Lockheed Martin was correct and moved forward. With that, we have a problem to kind of test to make sure you're able to do these conversion facts. The problem is, a solid rocket booster is ordered with the specification that it is to produce a total of 10 million pounds of thrust. If this number is mistaken for the thrust in newtons, by how much in pounds will the thrust be in air? Well, this might seem a little difficult at the onset. The first step of the problem is just to list the knowns. The question indicates that we're supposed to produce 10 million pounds of thrust. However, it's mistaken as 10 million newtons. We also know that 1 pound equals 4.5 newtons. With all this information, we can answer the question, by how much in pounds will the thrust be in air? The second step of the problem is to set up the first step of the problem. To do this, we have to multiply 10 million newtons by the conversion factor of newtons equals pounds. Now, using dimensional analysis, we put the newtons on the bottom here in comparison to these, so they match up and we can cross off the newtons. This leaves us with just the dimension of pounds. Doing this division with the calculator, we realize the answer is 2,200,000 pounds. The third step of the problem is to check and see if the problem was answered. If it is, why? The answer is that it is not quite answered because the question asks for the error in the equation, not just how much 10,000 newtons equals in pounds. With that, we can go to the fourth step of the problem, which is to finish it. In order to find the difference, we have to do the initial minus the final. We do 10 million pounds, which is what is asked, minus the 2,200,000 pounds that we found in step 2 of the equation. The answer is 7,800,000 pounds. The final step of the problem, the thing that these people did not do, is check their work. The first step is to see if it's logical. It obviously is logical because there's a big difference that would result in a thrust in air that would make the craft not be able to enter the satellite. Second is the question of if we have the proper significant digits. We started with 10 million, note the decimal point there, indicating that it's 2 significant digits, so the answer is yes. A quick thing to remember here is that you shouldn't look for significant digits at the conversion factor, but you should only look at your initial measures that you know. With this information, we can look at what could avoid consequences like this in the past. First is the most basic thing that we learned in the first week of chemistry from Mr. Collier, which is to use dimensional analysis, or the train tracks, as demonstrated in the second part of the question. By using this, we're able to make sure that we cancel out dimensions and not have any conversion errors. In addition, it brings up the idea that you should check your work. Reread the problem, ask a friend, double check the solution in the back of the book. By doing this, we make sure that we get the proper answer and we don't get the wrong answer on a quiz, or we don't make a mistake like NASA did, risking lives.
Alright, so our second problem deals with an issue between the metric conversion and the English conversion. And this was on July 23rd, 1983. Air Canada Flight 143 ran completely out of fuel about halfway through its flight from Montreal to Edmonton. Fuel loading was miscalculated through the misunderstanding of the new metric system that was just adopted in Canada. For the trip, the pilot had calculated a fuel requirement of 22,300 kilograms. There were already 7,682 liters in the tanks. So the problem is, if a liter of jet fuel has a mass of 0.803 kilograms, how much fuel is needed to be added for the trip? And so, step one is the information given. They give us that it ran out of fuel due to the newly adopted metric system. The pilot needed 22,300 kilograms. 7,682 liters are in the tank already, and 0.803 kilograms for 1 liter of jet fuel is the conversion factor. So step 2, set up the problem. We use our dimensional analysis and we take the conversion factor to convert the 7,682 liters into kilograms. And so we use a conversion factor of 0.803 kilograms and convert that to 1 liter, and that will give us 6,169 kilograms of jet fuel. Now we have to take that weight and subtract it from the necessary weight of 22,300 kilograms from what the pilot required. And that gives us 16,131 kilograms of fuel is required. And then, what we do after that is then we're putting the kilograms back into liters. So we take the 16,131 kilograms and use the conversion factor again of 1 liter to 0.803 kilograms. And that gives us a total of 20,088 liters of jet fuel is required for the flight. Now, our step 3 is just check the work. So is the problem answered? Well, the problem is asking for how much fuel is needed to be added for the trip. Yes, the problem is answered. 20,088 liters of jet fuel are required. Is this answer logical? Yes. And significant digits. Well, in the problem, it gives us 3 significant digits due to the 22,300 kilograms of jet fuel required. So we take that 20,088 liters of jet fuel and round up to get 3 significant digits. So roughly, for 3 significant digits, 20,100 liters of jet fuel is required. Taking this one step further, there was information not given in the original problem. Between the ground crew and the flight crew, however, they arrived at an incorrect conversion factor of 1.77 liters per pounds. This was the conversion factor provided on the refueler's paperwork, which had always been used for the rest of the airline's fleet. Their calculation produced 7,682 liters times 1.77 pounds per liter gave 13,597, which they interpreted as kilograms, but it was actually the fuel mass in pounds. Then they continued the calculation, which they subtracted the necessary kilogram weight, which was 22,300 kilograms, minus the 13,597 assumed kilograms, and that gave them 8,703 kilograms. Then they took 8,703 kilograms and divided it by the conversion factor, which gave them, or the conversion factor of 1.77 pounds per liter, which gave them 4,916 liters. So they were actually 15,172 liters short of fuel. And if mechanics and the refueling crew had known the correct conversion factors, this would not have happened, and the Air Canada flight would not have crash landed.
Conversion errors also apply to medicine, a field many Marquette students want to get into. For example, many pharmacists have confused in the past grains and grams. A grain is 0.003 grams. What this means is if they give someone too little medicine, they might not be able to treat a necessary condition like a heart attack, and the person might be at risk of dying that way. In addition, if they give them too much medicine, giving them grams instead of grains, they might risk an overdose from that medicine. Because of the health effect, it's very important for us to be able to tell the difference, and this is a very easy conversion mistake to avoid. The pharmacist or the doctor just has to make sure that they double check the prescription and give the proper amount of medicine.
There are also other problems that involve incorrect measurements and unit conversions. One of these being, at Tokyo's Disneyland Space Mountain, new axles were ordered for one of the rides, but the problem was they ordered the axles using pre-1995 English unit specifications versus the current metric ones, which really screwed up the ride and causing an axle to derail the roller coaster. And had they obeyed the correct conversion factors and not ordered the English units and followed the metric ones, this would not have happened.
The final scenario for conversion mistakes is also with airplanes. Oftentimes, shippers or people in charge of airplanes will make mistakes in confusing kilograms and pounds. This can result in one of two things. Either A, they underload the plane on a cargo plane and they lose money because they didn't ship as much as they could have. Or B, they overload a passenger plane with too many people or luggage and the plane can crash. This is obviously something that needs to be prevented. We wanted to end our presentation with the top 5 mistakes students typically make in conversion errors. The first is
forgetting to convert. You have to remember to list the solutions throughout the problem so that you don't forget to convert in the end or you don't forget any key conversion factors.
The second most likely error is dimensional consistency. The best way to remember this is to follow Mr. Collier's advice to use train tracks. Force yourself to cross off each individual thing so you get one final answer at the end.
The third thing is organization or forgetting to double check your work. You have to remember to make it a habit. If you don't organize or don't double check your work, you can forget something easy and screw up your final answer.
The fourth biggest mistake is two-part. It either is using the wrong conversion factors, like we saw in many of our examples, or assuming that the correct units are used. Now, the best way to remember this is to just list the units after the solution, which both save you points and prevent a conversion mistake.
And finally, the last most common mistake is significant figures. You have to remember to look back to the original question and remember the rules of significant digits so that you do not miss any significant digits. So if there's a problem with 3 and 4 significant digits given in the question, you want to use the least one. So you'd want to take 3 significant digits for your final answer.
With that, we conclude our presentation. Thank you for watching, and remember to always answer the question of how to prevent errors when this has been answered throughout the presentation with ideas like double checking your work or making sure you always list the solution with its proper conversion factor. And as long as you do these things, you'll save some points on quizzes. And if you ever go into the field of architecture or construction, you might save some lives.